Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Craig Zillis, who's a professor at the University of Illinois and has been there for almost 6 years. Craig reminded me that he overlapped with me for a year at Wisconsin. Can't say I remember Craig, but he has some good stories from when I was there. And it's a pleasure to welcome Craig. He's going to talk to us about hardware-software co-design, a very relevant topic these days.
Great. Thank you, Jim. As you said, my name's Craig Zillis. I'm from the University of Illinois, and I'm going to talk about some of my work today. And of course, this is work that I did with a number of my students. But it all kind of fits into this under this umbrella of hardware-software co-design for general-purpose processors. So I'm going to talk about 3 distinct pieces of work today. And by all means, if you have questions, interrupt me at any time, and I'm happy to address them. And I would love feedback and insults and whatnot. But I'm going to talk about hardware support for facilitating compiler optimization, a better, I think, hybrid transactional memory design, and hardware support for arbitrary profile collection. And although those are relatively distinct things, they all fall into the same sort of theme of hardware-software co-design. So I'm going to talk a little about that theme and sort of the research process that we take to do this kind of work. So the first thing about hardware-software co-design is I'm not claiming it's a new idea, nor that I invented it. But what it is that's recognizing that hardware and software have distinct strengths, and that if you build systems that are aware of those strengths, you can build systems that are better than just building, for example, software on top of existing hardware or hardware underlying existing software. And I'm personally interested in the general purpose computing context, and that sort of boils down to finding out what are the essential reusable primitives. And so in essential, I mean that you can't take anything more away from them and still be able to build the software systems that you want to build, and reusable in the sense that they're not just specific to an application. So they're not accelerators. They're useful for multiple applications. So again, it's not a new idea that historically the notion of hardware-software co-design goes back as far as instruction set design. And to some extent, instruction set design's fallen out of favor as people recently, in the last 15 years or so, realized that they could do most of the stuff that they wanted to do completely microarchitecturally. That is, without changing the interface between hardware and software, we could add the mechanisms that we wanted, for the most part, to improve performance and whatnot. But 2 things have been changing recently, which makes looking at rethinking instruction set and whatnot more interesting. The first being that power is increasingly becoming the primary design constraint, in that we could do everything in hardware, but it's probably not the most efficient way to do it. And so the multi-core trend is a big visible sign of this, but more generally, we're rethinking how to do things more efficiently. Secondly, there's a trend towards people writing software for richer runtime environments, for example, the Java Virtual Machine or Microsoft's .NET. And in those systems, we already have this kind of hardware-software layer running underneath applications. And so it lowers the barrier to rethinking the boundary between the hardware and software components that we already have there. So the idea of hardware-software co-design, again, is to draw on these complementary strengths. And the thing I want to point out is, in fact, that they are complementary. One of the big strengths of hardware is that you can add new parallel circuits that allow you to do things, add new functionality with very little or no overhead in some cases. And this addresses one of the main weaknesses of software, that often to add new functionality, you have to add overhead. In addition, hardware is very dynamic in that it can do small-grain, fine-grain decision-making at runtime based on application behavior and based on the current machine context, based on what resources are available. And this addresses another potential weakness of software, which is the rate that it can adapt to changing application behavior. But hardware has its own weaknesses. For example, we're not able to dedicate very much storage to retaining this kind of contextual information, and so we only get a very small picture of what's going on in the application, whereas software has the ability to do analysis and optimizations that have scope and effort that's effectively only limited by the amount of resources that we want to dynamically allocate to them. Furthermore, most of the optimizations that hardware can apply tend to be transient in that we might learn something about program behavior, but as we move on to another phase of the program, we'll forget that. And so if we come back to the first phase, we're going to have to relearn it. Whereas software, we can encode the optimizations as part of the executable, either by transforming the executable itself or annotating it somehow to carry that information. Finally, hardware, although it's very good at recording information about what's happened in the past, has little knowledge about what might happen in the future. Whereas software has the ability to do analysis, which is sound, and do things like realize that there's some operations that just won't need to be executed, which is something that hardware effectively can't do. So what hardware-software co-design, again, is understanding the limitations of hardware and software and building systems that address the limitations of hardware with software and vice versa. And so really what we do in this process is thinking about what can't we do with existing hardware interfaces, what is frequently done versus what can be done only once or statically, how little hardware can I require and still get the system that I want, and to what degree can the hardware we include be generalized for multiple uses. And really sort of boils down to thinking, what are the right primitives that if I provide these primitives, it'll enable us to build more interesting software systems, or better performance, or better reliability, or better efficiency, or whatnot. And the key challenge of doing this is that you need to understand both the hardware and the software very well. And so that leads to this methodology of identifying a problem area or opportunity, identifying a candidate primitive for that problem or opportunity, and then actually building the software system on top of it. And at that point, you can evaluate the system as a whole, and most importantly, you can go back and revisit the primitive and scrutinize to what degree you got it right, and what more you might need to add or what you can take away, that you can try to understand what are the true requirements. And so what I'm going to do is I'm going to walk through each of these three pieces of work that I'm going to tell you about and try to tell you what we learned from taking this research methodology. So again, the first thing that I'm going to look at is hardware support for simplifying the implementation of compiler optimizations. And this is work that we had in last year's ISCA and was also selected as one of 10 papers for the IEEE Micro's top picks in computer architecture. So the idea here is, well, a lot of architecture techniques either improve performance or reduce power. Compiler optimizations can do both, that they can improve performance by reducing the number of instructions on the program's critical path, as well as reduce power by reducing the number of dynamic instructions executed. And so it's a great lever for efficiency. And so the question we asked ourselves was, what could the hardware do that would facilitate compiler optimization? So our goal was to reduce the optimization implementation complexity, simplify implementing the optimizations. Therefore, more compilers would implement them, and even the ones that were already implementing these kinds of optimizations might implement them more aggressively and get more opportunity. And the key notion was that the need to verify compiler optimization is one of the things that limits its aggressiveness. For example, there's a number of optimizations that have been done in research but haven't actually made it into production compilers because of this verification challenge. And this work specifically focuses on speculative compiler optimizations. So the primitive we looked at was atomic execution, basically the hardware giving us the ability to execute a region of code completely and have it appear that it executed instantly or not execute at all. And so to interface to the hardware, we expose 3 instructions that serve as markers for the boundaries of this atomic execution. The first is a region begin instruction, which says, OK, this is the beginning of the atomic region I want to execute. a region end instruction that says go ahead and if you get to this point and commit this instruction, you can commit all of the instructions in between, and a region abort instruction, which if this instruction gets committed, it causes the whole region to roll back to the region begin instruction, restore the state as of that instruction, and transfer control to this alternate PC. And what this lets us do is it allows the compiler to generate code ignoring all the uncommon cases that the application could do but don't happen in practice. So for example, if we have a particularly hot path through the code as indicated by the red code, but there's an exit from this hot path to this cold code, what we can do is we can wrap the whole thing in this atomic region and transform this branch into a piece of code that asserts that the fall-through case is what's actually going to get executed. And that lets the compiler ignore this code completely for the purpose of optimizing the hot path. So that's the key thing we're enabling. And branches are one example, but there are other cases that we can also exclude by using these kind of insertions. So what we do with this, we've done this in the context of a Java virtual machine where it fits very naturally, but we're going to collect some profile information that allows us to identify the hot parts of the code. And so we go and we optimize those parts of the code, and we generate a hot version or fast version of the code which handles those particular hot cases, but maybe not all the other ones. So this might be sufficient for handling 99% of the code, and we're going to replace all the things that don't happen in practice with checks to verify that, in fact, that they aren't happening. In addition, we're going to generate a general version of the code, a non-speculative version of the code, that's going to handle those rare cases where the optimized version of the code doesn't actually apply. And so what this lets us do is take a very complicated piece of code, and where it has a relatively simple version is what happens in practice, whereas traditional speculative optimizations without hardware support has to handle potential exits from this hot path back to the non-speculative code. And this places two constraints on the compiler. One is these exits from the hot path can potentially limit the degree we can optimize the hot path. And in addition, we have to correctly generate any fix-up code necessary for converting the state from this hot code to the cold code. And getting that right in practice can be challenging. And so what the atomic regions do is they greatly simplify this process, because all of those things, all those potential exits from the hot path get converted into these abort statements, which then roll the whole region back to the beginning. And at that point, we can transfer control to this code. And so there's really only one exit from the hot code that we have to worry about. And that's at the very beginning before we've changed any state. And so that case can be handled trivially. And what that means is we can take this piece of code that originally had 100 exits from the hot path, and we can reduce it down to a much simpler piece of control flow that only has 5 basic blocks and 2 branches. And having done that, we can apply existing traditional formulations of optimizations, and they're now able to get the speculative optimization potential, or at least a bunch of it in this code region. Question?
How do you handle optimization which are dependent upon the special data? Like, if the variables are all unaliased, you can do the code this way instead of...
So we can put a check that specifically checks to see whether that aliasing they are not aliasing, in which case then we can assume that they are for the whole region. Does that make sense?
I think when you've got 10 different variables, it may be hard to put 10 to 2 different assertions.
So you're right, there's potentially, if I have to worry about all the potential interactions, that's not something that we've heavily exploited. There's potentially other hardware mechanisms that would be more efficient for detecting whether various variables alias. My guess is that you can get a bunch of the potential without having to do the full cross product of that, but I'm not willing to guarantee that that's the case. Is there more that you wanted to follow up on, or? Okay. Okay. So that's the goal of what we're doing. I'll talk a little more about the hardware primitive. Again, we have exposed these 3 instructions, and what they're doing is the atomic begin is taking a register checkpoint. We're actually doing that in a more efficient way, assuming an out-of-order machine by checkpointing the register rename table. But that's just a hack to get this to be lower overhead. In addition, we want to make sure all future memory operations are speculative. We want to be able to roll back stores in particular. And so we do that by adding speculative read and write bits to each cache line. And this is a pretty standard trick in the architecture community, which has been used for thread-level speculation, speculative lock collision, and hardware transactional memories. Assuming we get to an atomic end and we can commit that instruction, at that point we will commit the whole atomic region, in which case we can discard the register rename table checkpoint, commit all the speculative memory operations, basically doing a flash clear on all these bits, and those values become visible, and the whole region's committed. Or if we commit an atomic abort instruction, then we restore the rename table checkpoint with that alternate PC, and we're going to discard all the speculative memory writes. So basically any block in the cache that has this write bit set, we're going to invalidate. And so we've thrown away that speculative value. And the key is, or one of the keys, is that if in addition we raise an implicit abort and do this same process, anytime we get a coherence conflict, we get atomicity out of this. So if another thread accesses a line in the cache that we have read or written, and their coherence request causes us to downgrade such that we can't retain read or write permission, then we abort ourselves because somebody's potentially trying to peek at one of our variables while we're executing. So by doing that, we guarantee atomicity also, which allows us to reorder operations and not have to worry about thread safety as long as we preserve uniprocessor ordering. Question?
In the speculative optimization application of this, have you thought about doing anything special if the transaction aborts for capacity or conflict reasons, as opposed to an explicit abort for a test for the conditions for staying on the hot path?
Yeah, so let me answer this slide and then I'll get back to your question, or talk about this slide and then I'll get back to your question if I can. So what we're assuming in this hardware is that it's best effort, that it's not going to guarantee that any particular region of code is going to make forward progress. And what that does is it greatly simplifies implementing this from the hardware designer's perspective, that the hardware designer can decide that we're going to abort this region for any case that might be complicated. And so one obvious ones that would be hard to implement is handling I/O atomically, dealing with interrupts, and in particular, limited buffering. So we're only going to support, for example, what might fit in the L1 cache, and not propagate all of these bits down to lower levels of the cache. And one of our findings, which is relatively, I think one of the more interesting findings, is that we can build compilers that are very tolerant of this best effort atomicity. That basically we try to select regions that are either acyclic or are very likely to cycle a short number of times, such that they will almost always fit within the available buffering. And so to get back to your question, we try to avoid that problem proactively by not selecting regions that are going to overflow the cache. And I guess I can't quantify to what degree we're sacrificing performance by the region selection that we are doing, but I guess we're able to get significant performance in the presence of the region selection that we're doing. Does that address your question? Any other questions? Yep.
So if it goes through this fast path, then you're going to get an atomic memory operation. But if the fast
or all of the memory operations are going to appear to all of the threads as if they happened all at the same time.
Right, but if it ends up going down the slow path for any number of different reasons, software or hardware reasons, then it won't be atomic. What do you feel about the risk that this might actually cause people to write software that instead of working right 99% of the time, works now 99.99% of the time, because now it has to go down the slow path and have another thread touching the memory at the same time to fail. So therefore, you're personally making software less robust.
It's an interesting question. So certainly, Louis Sezzi at the University of Washington has a paper that says if you have an execution model where they tend to chunk things and commit them atomically, it can mask these race conditions at some frequency. So that's a paper that he's presenting at ISCA this summer. So certainly that effect would be present. I don't know what to comment to it. That certainly it could be a negative byproduct of this, but I'm not sure it's worth throwing out the baby.
If you knew that the hardware transaction aborted because of conflict, you could have a mode in which that raised an exception as a race condition again.
Okay. So certainly and I'll talk about this in the next section, we assume that we can know the reason why something failed and therefore transfer over to software to handle things differently. So when I talk about the transactional memory system, that is a very important piece of that.
Well, I guess the observation here is not so much carrying on, but raising the debug exception so that the problem gets fixed. Because there probably should be in the program hard locks of some sort.
Could be, yeah. So that's if.
Seems like it increases your test effort because you've got now two paths that you have to explicitly test for, essentially.
So I guess so. We really aren't. One of the impressive things about this is we didn't change the compiler much except for region selection, and I think that that'll be in a couple slides later. So yes, you could imagine that we have, to some extent, the same problem that speculative compiler optimizations have, but less so. So the problem with speculative compiler optimizations, if I go back to this slide, is I have all of these potential paths that I would need to test. And so IA64, this problem comes up in spades. So yes, we have this path, that I guess you could force the compiler to not generate these code regions or cause them to force them to abort and do all your testing on this. I don't know if that would be any worse than. So given that primitive, we went ahead and built a software system on top of it. I kind of want to give you an understanding of what the system does, and I'm going to use this piece of code as a running example. Basically, again, we did this in the context of a JVM, and I've got two methods here. One called foo that has this loop in there that's infrequently taken, and it also calls this method bar, which happens to be a synchronized method in Java. And so there's this monitor entry and monitor exit, which would acquire a lock and release the lock at the prologue and epilogue to guarantee the isolation of the execution of this code. This function also calls another function as well as potentially throws an exception, which if the exception's thrown, we have to release the monitor before we unroll the stack and whatnot. So this is a piece of code, and the first thing our changes to the compiler have to do if we want to take advantage of these atomic regions is select the region that we're going to do the optimizations on. And so this turns out to be a bit of an interesting thing by itself because we want the regions not to be too small, because if they're too small, we don't get a lot of optimization benefit. We don't want them to be too large, because if they are, they might overflow the cache. And we want to get good coverage across the whole execution. Then we want most of the code executed to be within atomic regions to get the benefit of these optimizations. And so we have an algorithm for doing this, but in general what it does is it picks the hottest path through regions of code and tries to estimate the dynamic instruction length of those paths which turns out to be a reasonable proxy for how much optimization potential it is, as well as how much data they're going to touch. And so it tries to size them appropriately in such a way that we get good coverage. And so I'll refer you to the ISCA paper if you're interested for the specific algorithm. But for example, it would probably select both of these methods to be within a single region, because the hottest path through this code goes through this bar method and takes this particular path. It's acyclic, so it's not going to run very long. And then it takes this path. And that's certainly going to be small enough to fit within the cache, but might give us some optimization benefit. We might also inline this into the previous method also, but that didn't fit on the slide. So step 2 is to identify what's cold. And so for the purposes of the system that we built, we had a static bias that was anything that's executed less than 1% or had a bias of less than 1%, we'd cut out. So for example, this method is executed less than 1% of the time we reach X. Also, this back edge from C to B is executed less than 1% of the time we reach C. And we're also going to cut out any hardware exceptions, because our hardware support for atomic regions doesn't actually handle exceptions. That means that we don't have to handle the exceptions in the code that's generated. So the potential for Y to have a hardware exception is not going to, in practice, be a barrier to optimization for us. So step 3, once we recognize what's cold, we're going to trim off all that cold stuff, and then we can inline and unroll at this point. And one of the benefits we get here is that we effectively get partial inlining and partial unrolling for free. The last step is to take all of these little pieces that we left hanging and deal with them by converting them to asserts. So for example, we're going to assert that X bar is actually going to go to Y bar, and so that shows up in our code. Similarly, C bar to D bar. Also, these monitors, since we're going to wrap this whole thing in an atomic region, we don't actually have to handle the monitors completely. So we do some profiling to say, is in fact this monitor not accessed or not contended for, in which case we merely need to check to see whether the lock is free. And so this is sort of a software-controlled speculative lock collision. And what it does is it both reduces the amount of single-thread overhead, that this check is cheaper than the lock acquire and release, and it also is no longer a barrier to optimization. So we can move code throughout this block however we want. And then we wrap the whole thing in an atomic region. So we insert the A region begin and A region end nodes and point them to the previous flow graph for foo. And so you can see that we've effectively got this partial inlining, that we've inlined in the hot case and not in the cold case. So that limits the amount of code growth due to inlining. Any questions on that?
So there's some things, when you first described it, there were exit conditions where you could imagine implementing the same optimization in software by restoring from the state on the hot path to the state on the cold path, and then it resumed the cold path in the right place. At least one of these, like the assert monitor is free, is something enabled only in this case. Are there other examples? Like you could imagine doing writes before the place where you...
Well, so for example, we have the freedom to, I guess some of it comes from, the multi-thread safety, that we're free to reorder memory operations to distinct memory locations, independent of the memory model, because they're going to appear all in the same place in the total memory ordering.
If there were a write in Y prime that would
I could push that down here, or I could hoist it up.
But does the compiler you're using do that, or?
So I don't know to what extent we didn't touch the scheduler, so we're very careful that we don't hoist things out of the region, because we had that bug and it caused problems. But I don't know to what extent, we didn't specifically try to improve it, but now certainly the monitor boundaries are no longer preventing scheduling, which they do in general in Java. Other questions? So again, what I think was one of the most interesting things that came out of this piece of work was how easy it was to implement in the compiler. That it turns out that the support for having this one version of the code that fails over to the other version of the code, there's already something like that in the compiler to support try-catch. And so basically we took that mechanism and overloaded it. We took the recovery edge for the try-catch or recovery edge for our stuff and mapped it to the exception dispatch edge in the internal representation. So the control flow is handled already for us. We had to add a new virtual instruction to the intermediate representation to handle these asserts, but it turns out to be very simple. It's basically an add instruction that doesn't produce a value. So it's a single non-control flow operation in the IR, and once we defined it, it turns out that the existing passes already operate on it because it just looks like an add, and the partial redundancy elimination says, oh, if I have two of them that have the same inputs and doing the same operation, I can remove one of them. And I can schedule these freely throughout the code just as if they were adds that nobody used the value of, but I can't dead code eliminate them. So that was neat. Turns out most of the complexity we add was because of this region formation, and we could do that in about 2,000 lines of code. And once we did that, we could take the existing optimizations without modifying them, and they could find new opportunities for optimization. So again, we were surprised at how easy this was, and I claim it's significantly easier than if you implement speculative optimizations without this hardware support. So we evaluated the system. This is work we did in conjunction with Intel. So we used the Apache Harmony JVM, which is an open source JVM that Intel was significantly interested in. They were doing a lot of the development for. And we used their infrastructure for doing full system execution-driven timing simulation. So we simulate the hardware and did Pentium 4-like microarchitecture. Again, the model came from the Intel people. We used standard Java benchmarks, the Da Capo suite. And one of the challenging pieces of this work was how do you sample the execution of a program when the code is generated dynamically by two separate compilers. And so it was quite a bit of work to get a methodology that worked for this, but basically we insert in specific Java methods a little marker, and the simulator keeps track of how many times it's seen that marker go by. And so we can select the same region of the execution in two runs of the program, assuming the program's largely deterministic in its execution. So that allows us to do an apples-to-apples comparison. And what we get from, and I say our first pass implementation of this, so again, this was not a huge amount of effort went into this compiler, and we were still able to get about a 17% on average speed up from this, and a 14% reduction in the number of micro-ops executed. So again, the number of reduction in micro-ops is a relatively good proxy for reduction in power, that the number of, or reduction in dynamic power at least. And so that's the first point, but you can see that the performance comes from different benchmarks differently. And in particular, I want you to focus on this case where we get a slowdown because I know why we get it, and I think we can make it go away. The key there is for that benchmark and a couple of others, we're getting a non-trivial number of these regions aborting. That in general, we like to see much less than 1% of them dying. In this case, we're getting on the order of 2% dying, and that's causing a lot of that's causing this slowdown. And what that's due to is that some branches, over time, their bias changes. So initially, we're profiling the execution, and we say, aha, we found a branch that's highly biased, and so this is something I want to optimize. But as the execution goes on, the behavior changes, and now we're aborting every time we execute that region. And so this is a relatively easy thing to do, and this is one of the things we're doing now, is building the system that recognizes when behavior changes and decides when to re-JIT the code and generate a new version based on this. So the other thing that we learned in doing this is the compiler is the implications it has on the hardware. The compiler we built generates atomic regions that are relatively small after we've optimized them. So we select regions, and the optimizations tend to be relatively effective. And so they get down to tens or hundreds of instructions. And so this has two implications. The first is that if it's happening very often, that it has to be fast to take a checkpoint, and it shouldn't stall the pipeline. And so if it does, if we, for example, have to spend 20 cycles taking a checkpoint, that basically gets rid of all of our potential benefit. Similarly, these regions are small enough that multiple of them will fit within the instruction window of a modern out-of-order processor. And so the hardware has to be able to support multiple of these atomic regions in flight simultaneously. That if I stall at a begin every time I'm waiting for an end to commit, again, I lose all the potential optimization benefit that we've found in our studies. So in summary, atomic execution makes trivial the implementation of these speculative optimizations. Basically, we have few changes to make to the compiler to get this benefit, and it also simplifies adding new optimizations, like this partial inlining and partial loop unrolling. It's amenable to high-performance hardware implementation because we're not basically, and I'll mention in 2 slides later, there's already multiple companies that have built hardware primitives like this. The Azul and the Sunrock have hardware that's somewhat similar to this. And we can get pretty reasonable performance and reduction in number of instructions. And by adding dynamic feedback, we can do even better. Question?
When you're enabling new optimizations but not changing the old optimizations, is this 10 to 17% speed up because of the new optimizations?
It's some of each. So it depends a lot by benchmark. You'd probably want me to estimate the fraction of which is which, and I'd be afraid of doing it. So actually, the results we ran these results 2 different ways. Because we had this partial inlining benefit, we were concerned that a lot of our benefit was coming just because we were inlining more code. And so we compared the base inliner, the benefit we got from the atomic region optimizations versus the base inlining versus just inlining a whole lot more. And it turns out that we beat that case by a little. That basically we hugely cranked up the inlining threshold so that it would inline everything it could. We still outperformed that. And then I think what's more telling is if we ran the atomic region optimizations with this very aggressive inlining, we actually got, and I have the data somewhere else, the performance that we got was actually larger than the sum of the inlining and the atomic optimizations by themselves. That by having the aggressive inlining, it exposed even more opportunity for the atomic regions to get optimization benefit. I don't know if that at all answers your question. I wish I had off the top of my head numbers, but the thing is they vary a lot by benchmark. There's some benchmarks where there's a lot of synchronized methods executed, and so the ability to remove that overhead was significant. There's others where that's totally not important, and so trying to recall an average is somewhat difficult. Ben, did you have a?
So the baseline compiler was a JIT compiler.
Yeah. So this is
Yeah. So did it have multiple sort of levels of optimization?
Yeah. So this is implemented in the second level. So basically, we don't care so much about the performance of the first level, and we're using that level to get the profiling information necessary to do our optimization.
And the results here. So, okay, I think I figured it out.
Okay. Sorry. So the second thing, people are willing, that I'll talk about is building hybrid transactional memory. And the goal here is, in my mind, getting the best of both worlds, which is we want fast common case transactions while retaining the ability to fail over to software for things that the hardware doesn't want to handle. And this is work that we're presenting in this year's ISCA. So I'm going to assume, does everybody know transactional memory or heard of it? Okay. So most of you have probably already recognized that this notion of atomic execution that I've been talking about has a lot of similarities to hardware transactional memory. And that's part of why we think that work's interesting, is because potentially it allows you to build one mechanism that can support a lot of things. So again, so basically what this atomic execution lets you do is, if I have this atomic statement at my source level, I can just translate it directly to a transaction begin, a load, and a store, and a transaction end. And just by holding shared coherence permission for things that I read and exclusive coherence permission for things that I'm writing, if I can hold those until I commit, then I can commit my transaction. So this is, again, relatively simple to implement, and this is what Azul and Sun have implemented. The problem why it's not the end of story for transactional memory, among other things, is the limitations. That it's limited to the size of the hardware structure that we're going to allow to do this. It can't support context switching, and perhaps it doesn't support all of the semantics that you might want from a transactional memory programming model. There's a number of hardware transactional memory proposals that try to go beyond this simple hardware transactional memory, sort of Herlihy and Moss interface, but they get kind of nasty. And given that architects to date have been unwilling to even give double compare and swap to this point, the thought that they're willing to guarantee forward progress for arbitrary sized transactions and very long running, and worrying about operating system virtual machine running underneath you, dealing with page faults, whatnot, I'm not optimistic that they're going to give everything. And so I'm not sure all this is going to happen anytime soon or at all. So the alternative to the hardware transactional memories is software transactional memories, which, again, I'm going to largely assume people know about. Is that a fair assumption? So I'm going to talk about it a little, just because I'm going to talk about the one that we use in our work in particular, and we can argue about that. But basically, the idea is we want to do conflict detection and handle rollback in software. The rollback we can handle by write logging, that before we overwrite a value, we record the old version. So this is an eager update STM that I'm assuming. And do conflict detection, if assuming a word-based STM, by maintaining an ownership table. And so if we want to access a variable within a software transaction, we can take its address, hash it to some location in this ownership table, check for conflicts, and then attain ownership to that line. So the key thing about software transactions is they don't have the virtualization problems that hardware transactions do. You can have very large ones. They can run very long. They can do I/O. You can do crazy nesting models and whatnot. They have all the flexibility of software. The problem is they have all the overhead of software too, potentially. So when you translate this atomic statement, typically you might have to save some state at the beginning of the transaction, maybe registers, maybe not. And then before the first access to any piece of memory, you have to add a read barrier if it's a read, or in a write barrier if it's a write. And these are going to do these lookups on the metadata and potentially write state, as well as do logging if necessary. And then when we end the transaction, we have to walk our logs and go and release ownership to these various things. So the key is that all of this costs something, and so that adds overhead to the transactions. And also, it makes it undesirable to do all of this for the non-transactional code. And so typically you get what you might call weak atomicity, in that you don't detect conflicts between non-transactional code and transactional code. So there was a neat idea, which was this notion of hybrid transactional memory, that says, let's try to get the best of both worlds. Let's try to get hardware performance and software virtualizability by running small transactions in hardware. Hopefully that's the common case. And then running things that don't fit in the hardware and software. And hopefully that's uncommon, but we can still make forward progress. This is a great idea, except there's one challenge, which is detecting the interactions between the hardware transactional memory and the software transactional memory. So between the hardware transactions, we can detect conflicts using the coherence protocol. We detect conflicts between the software transactions using the ownership table. Software transactions can't break the isolation of hardware transactions. That's not in a case we have to worry about because, again, the hardware transactions are strongly atomic. And so if a software transaction tries to access something that's part of a hardware transaction, it'll break its atomicity and force the hardware transaction to roll back. The key problem is keeping the hardware transactions from breaking the isolation of the software transactions. Specifically, making sure that the hardware transaction doesn't read some stale data of the software transaction, or that the software transaction doesn't read a value before and after a hardware transaction is committed a new value. And so the solution that the original hybrid transactional memory proposed was to have the hardware transactions snoop the ownership table. And so what this entails is adding read barriers of a sort and write barriers to the hardware transactional memory version. And the drawbacks of this approach are twofold. One is, although the hardware transactional memory gives us strong atomicity, the atomicity of the whole system, even though most of our transactions might execute in the hardware, we can't assume anything. We can only assume weak atomicity for the whole system. More importantly, we've added this overhead to our common case, which is exactly what we didn't want to do. So this is what we're going to try to address and get zero overhead common case transactions. And the way I'm going to do that is by adding fine-grained hardware memory protection to the list of available hardware primitives to our system. So I'm assuming a low overhead fine-grained memory protection mechanism. And what this means is, by memory protection, I'm assuming, much like virtual memory page protection, what we're getting is the ability to get notified before we access a protected piece of memory. And that memory protection should not just span what's in the cache, but should span potentially out to disk. It's fine-grained in that we want to protect granularity smaller than a page. And for our application, at a granularity cache block suffices, because that's the granularity that the hardware transactional memory is going to be running at anyway. And it should be low overhead. Especially, we want very low overhead checking of these permissions and relatively low overhead of registering and deregistering protections. And so the design decision we've made in this case is that it should be user mode to set these privileges. And so we avoid any system overhead of doing a syscall to do that. But that means it's effectively a cooperative mechanism, that it's not useful for security purposes. But I'm somewhat agnostic about this design decision. But the point is, what I'm interested in this work is demonstrating what you can do with this fine-grained memory protection. To do the work, we had to assume one particular implementation to study. But I'm, again, agnostic on the particular implementation. But what we use is a design called UFO, or what we call UFO, which is an acronym for user fault on read and user fault on write. So what we assume there is that we can steal a couple bits from ECC by re-encoding ECC at a larger granularity. And so we free up 2 bits per cache line. And those 2 bits, we have a fault on read and a fault on write bit. These live with the cache. So whenever the data gets moved around the system, these bits go with it. We keep them coherent by allowing them only to be written when you have exclusive permission for that line. So only when I know I have the only copy of this block can I actually change these bits, and then when other people request it, they're guaranteed to get the same value as everybody else. So again, these bits move between caches as well as into memory, and we store this data in ECC in main memory. In addition, we can page those bits out by, we've made small changes to Linux so that when it pages things out, it goes and harvests those bits, stores them on the side, and when it brings the data back in, it puts them back. And this adds negligible overhead, except in the case when you're already hugely thrashing memory, and this is the least of your problems in that case. And so what happens is we access data normally. As we're accessing data, we read these bits also, and then at retire time, if we're accessing a piece of data that has one of these bits set, and we're accessing it in a way that conflicts with that, we get an exception at retire time, and that invokes a user handler. And so we can then do whatever we want at that point in software. So that's the primitive. We built a software system on top of that. So what we did is we added UFO support into the STM to make the STM strongly atomic. And so what we did is that transactions set these UFO bits when they acquire ownership. So when in these read barriers, for example, it'll set the fault on write bit for the block that it's reading. And in a write barrier, it'll set both the fault on read and fault on write bits. And so what that gives us is that non-transactional accesses that would otherwise break the atomicity of the software transaction get prevented from completing. Does that make sense? So thereby, we get strong atomicity, and to avoid getting spurious UFO faults from an STM transaction, the STM transaction turns off the fault so that it's protected its own data, but we don't want to get faults when it's accessing its own data. And conflicts between software transactions are already going to be detected by the ownership table. So the key is that these UFO bits don't introduce limitations on the STM in terms of its virtualizability, for example, in that they're persistent, that we have them for all of memory, so that's not going to limit the transaction size. And they're also not part of the core, and so we can context switch without problems. So in this implementation, to make the implementation somewhat simple, we've implemented our ownership table at a cache block granularity. And so that means we just need to set and clear these bits whenever we create an entry in our ownership table. And that's when we set a bit, and we clear a bit whenever we remove an entry in the ownership table. And so one key that for anybody who's familiar with STMs, this effectively requires us to do visible readers. There's no other software maintenance beyond the ownership table, so that's all we need to do to keep track of when to set and clear the bits. And this means that there's negligible overhead beyond our baseline STM. And so that's just what this graph shows, is the black is our STM without UFO support, and the gray is the STM with UFO support. And you can see there's not much difference, but the STM does have a certain overhead to begin with. Again, that's why we have the hybrid transactional memory. So in particular, it's nice that it's negligible overhead, but I'm really not that concerned about the overhead of the STM because my goal is to get most of the transactions executing in hardware to begin with. That the STM is sort of, hopefully, the last best hope. Question?
Could you explain again why it requires visible readers?
So I need to set the bits whenever, I need to set the fault on write bit whenever I'm reading. And I need to know when to clear that bit. And so I need to know when I'm the last reader leaving. Does that make sense?
So you need to know there's different levels of visible readers if there were just a count and a pessimistic.
Yeah, so a count would be sufficient for knowing when to clear the bits. Knowing who they are is necessary if you want to do contention management. But that's sort of a standard STM issue. Good question. So what adding these UFO bits does is it enables our hardware transactions to avoid these read barriers. And the reason why is because with the STM being strongly atomic, that if the hardware transaction tries to access something that the software transaction is accessing, it'll receive this fault and prevent it from breaking the software transaction's atomicity. So this is our main goal, is that, again, we get back to this uninstrumented hardware transaction that can run at full speed. Does that make sense? So there's one potential caveat, those of you that are paying attention. Setting the UFO bits requires write permission. Even if the STM is only reading. So that means we potentially have false conflicts with the hardware transaction. That I can have two transactions just reading a line. And the hardware transaction has shared permission for it. The software transaction, when it's setting the bit, has to acquire exclusive permission. And so it has to invalidate the hardware transaction. It turns out we were worried about this. We were all prepared to solve this problem. And the problem never showed up, at least in our workloads. So we've done some sensitivity analysis to say, what if we could magically set these bits without acquiring permission? And everything got 1% faster, but we decided 1% was fine price to pay for not having to change the coherence protocol or do something nasty. I think in practice, there's software solutions that would potentially solve this if it was a problem. That my guess is this would largely be a problem on widely shared data, which was infrequently written, in which case you could set the bit the first time and then lazily clear it when you actually had somebody that wanted to write it. so that the last reader doesn't actually clear the bit when it leaves, because the conflict only occurs when you set or clear the bit, when you need to write the bit, that we can have as many software transactions reading this as long as we don't transition from having 0 software transactions to having 1 or more software transactions. I don't know if that makes sense. But I think that's also the main reason why it turns out not to be a problem in our workloads. So again, we evaluated the system. We built a library-based STM. Currently, it's very blocking, and that's not so good if we actually had threads swapping and whatnot, but it was easier to build. At the moment, we're trying to resolve that by, you can ask me offline if you're interested. Its performance is pretty similar to TL2, which is a contemporary STM. We also built a simulation of the hardware. This is our own full system multiprocessor timing simulator. Again, we use processor parameters that are representative of modern processors. We use the stamped transactional benchmarks, doing full benchmark runs because they're relatively short programs. And we compare to an ideal HTM. So this is what if we could do everything in hardware and still have arbitrarily sized transactions and still be able to roll back an aborted transaction in a single cycle. So this is kind of an ideal upper bound, probably unrealistic upper bound, as well as 2 previously proposed hybrid transactional memories. So the one that I mentioned here, and then phase-TM. Phase-TM says we'll solve that problem by allowing only hardware transactions or only software transactions at any time. So I'm not going to show you all the data. I'm going to show you, I think, the most interesting part of the data is the case where we actually have some transactions overflow. So the key points of pieces of data are that our UFO hybrid, this gray triangle, performs almost identically to the unbounded in almost all the cases. So in this case, it's pretty much identical. In this case, it's pretty much identical. And only in this case, where there's a non-trivial number of transactions that have to execute in software, do we get much of a divergence. And basically, this is almost as good as we could do, because fundamentally, if you have transactions execute in software and there's an overhead for executing transactions in software, that's going to cause you to lose some performance. The key is that it's robust, and you can't really see this from this graph, but the fact that some transactions are running in software isn't preventing the other transactions from running in hardware or harming them. The other hybrids, however, even when things don't fail over into software, for example, the hybrid TM scheme has some overhead that's causing it to perform somewhere between the software transactional memories and the hardware transactional memories. And in particular for phase TM, when there are a non-trivial number of transactions failing over to software, that causes all of the transactions to fail over to software in the regions where there's at least one transaction failing over to software. So you actually see this point where you actually the performance goes down as you have more threads executing, because you're more likely at any given time to have one transaction that has to execute in software, which hurts everybody else. Are there questions on that? So I'm pretty pleased with these results, but I think what's arguably more interesting is what we need from the primitive in order to get this to work. One is, the first lesson we learned was that good contention management between hardware transactions is fundamental. So in our scheme, we used age ordering. We eventually settled on using age ordering because we first tried requester wins, and this is what I believe Azul and Rock are both implementing, which is much simpler. It basically says if I have my transactional working set, and if you come along and request something that I want, that I have, I give it to you and I kill myself. So the requester wins. The problem with that is you have potential for live lock, and also just a lot less forward progress is being made. And so it's guaranteed to be more complex to support some sort of better contention management policy in hardware, but what our results suggest is that gives you about a factor of 2 in performance. And so it's probably worth doing. And so I have some ideas of how we could do this. We implemented this somewhat magically in our simulations, but we think we have a way of of doing this that's not so bad. The second thing is that it's important never to fail over to software if you can at all avoid it. In particular, you don't want to fail over to software due to conflicts. And the reason why is if you're failing transactions to software because of contention, you're only going to aggravate the contention. And so that's less of an effect, but still, so basically this is saying, oh, if I fail 5 times, I'm going to fail over to software. And so we picked this because this was the policy that the hybrid transactional memory used, because they had to do this to make forward progress, because with the requester wins, otherwise they had live lock and their applications never ended. But it's important, if you can avoid doing this, that'll save you 10% of the time. The key is you need to know when it's necessary to fail over to software and when it might not be necessary. And so the key to doing this is having a piece of code between when you try it in hardware and you fail over to software to decide, should I try this in hardware again or should I fall through to software? And so again, this comes back to the point we had before. You need to know why you failed. That if you failed because of overflow or I/O or system calls or some application exception like a divide by zero, it's very unlikely you're going to succeed if you retry in hardware. In contrast, if you fail due to a conflict or an interrupt, it's very likely that you're going to succeed if you retry in hardware, especially if you have some sort of backoff implemented to reduce the contention. Finally, if you have some sort of system exception like a page fault, you're likely to succeed if you retry in hardware if you first do some work. So for example, if you bring the page into memory and then retry in hardware, you're likely to succeed. And so the hardware we settled on records when it aborts the abort reason. It also counts the conflicts so that we can decide when to do backoff. That if we get one conflict, we might not want to bother with backoff, but if this is our 5th conflict since we committed a transaction, we might want to do some backoff that's a function of how many conflicts we've had. And also records the kind of system exception happened and address so that we can poke that piece of memory, bring it into memory, and retry the transaction in hardware. So assuming there's no questions, and feel free to ask questions, what having the software transactional memory plus UFO plus these atomic regions gives us is the ability to do full-speed common case transactions, have strong atomicity for all transactions. We still have the ability to fall back to software to handle arbitrary size transactions and context switches. And it also, and this is something that we're playing with now, allows us to evolve the semantics of the transactional memory. So in particular, one thing that we've been playing with is trying to implement this kind of retry primitive where I wait on a bunch of things using the transactional memory system. And so we have an implementation that runs in the STM, and by being a little smarter about the hardware, by allowing the hardware to receive the UFO faults and not destroy its atomicity, we can actually get hardware transactions that can wake up software transactions without aborting themselves. So that's something that we're playing with now. But in general, what we'd like to believe, part of the reason why we're doing this work, is that this structure allows us to evolve the semantics of the STM without having to change the specific implementation of the hardware. And one point is that this whole thing is built from hardware primitives that are useful beyond TM. That in particular, these atomic regions are useful, both for doing speculative law collision as well as the compiler optimizations. And hardware fine-grained memory protection, I think, has a lot of uses, including scalable watch points as well as concurrent garbage collection applications, ensuring invariance for other speculative optimizations, things like that. So I think it's potentially a very costly primitive for the hardware to provide, but I think if it does provide it, there's a lot of software systems that can use it.
What do you think it's costing?
So you go to the hardware people and they say, oh yeah, you want 2 of those ECC bits? So does everybody else. And so the key, I think, is, and this is one of the things that we have for future work, is figuring out how we can expose those bits so that lots of people can use them simultaneously. So effectively virtualize them and use them for multiple purposes simultaneously without causing the whole system to bog down. So that's one of the reasons why, effectively we're assuming that, in the future, all machines are going to run with ECC, so we can steal these bits, because if they aren't, then we can't. The other thing is, and this is a little subtle, that if you're not running with sequential consistency, there's a little bit of a challenge, which most hardware isn't, that you need to be able to look at the bit before you commit the store to the line. And often you commit a store without actually having the line. And so you need the ability to commit a store and say, oh, I shouldn't have done that, and roll that back. But it turns out that has a lot of similarities to the hardware support you need for doing atomic execution. And so we believe you can overload those same mechanisms to give you the ability to be able to do stores and then undo them. So there's some nastiness there, but I think if you just go to the hardware people and say, look, here's this application, they'll say it's too expensive for what you want. But
so two questions. Why do you think ECC is going to be widely available in the near future?
Why do I think it is? I'm not claiming that it is. I'm saying again, this is one particular implementation for fine-grained memory protection. There are others. I'm not claiming that it isn't. Half the people I talk to say that it might hit. There's some point where it makes sense that as transistors get smaller and smaller, eventually it's going to happen. I don't know when that time is. Some people say that it is in the next 5 years. Other people say it isn't. I'm not an expert enough to say one way or the other. So that was one question. What was the other question?
Well, and then the other point was, if they do become widely available, what's the cost of a few extra bits at that point, right? Because you're saying they're going to be used for a number of different things, right? So there's sort of there's a transition where, once people agree that they're going to change the structure of memory.
Well, so it's not where, so ECC memory already exists, right?
Right.
And the question is, and this trick is well known of sort of how you can re-encode ECC, that the DEC Alpha 21364 did this trick to store its directories in memory. The trick is, that there's a lot of people, who would love to have these bits for various, security, whatnot, and so so far they're not, they're not there. But there's a long list of things that you could use them for, and so how do you decide which bits to allocate to whom is a challenge. It's a scarce resource. So, but I think especially if people are going to continue programming concurrent programs with, the current raceful programming models, having some bits to track accesses to memory will be useful for building tools for, race detection and whatnot, debugging in context of control. I think there's a lot of neat applications if you expose some of these bits to the programmers. And so the key is exposing them in a way such that it's not like you can use them for this or this at any given time, because we're going to want to run lots of tools simultaneously, potentially, or tools or system services. So the last thing I'm going to talk about, and it's relatively brief, is hardware support for software instrumentation. So basically how we can get arbitrary program profiling almost for free. And this is work that we had in CGO, which we presented last week. But the neat thing is, based on preprints of this, 2 companies have also already told me that they're planning features in new processors that were inspired by this. So it's pretty cool. So the gist is that increasingly people are building software systems that want to monitor themselves for some reason or another. And so one common way that gets done is by instrumentation. So for example, Google in their search engine, in their deployed search engine that you use, collects at least 2 kinds of information. One is the size of heap allocated objects, and they log this so they can, and also the allocation site so they can figure out where they're allocating memory. And periodically, when they get lock contention, they pull a whole stack trace. and they log this. And this is information that they use to do performance analysis on their deployed software. The thing is, these are too expensive to collect all the time, so what people typically do is sampling. So they have their instrumentation code, and they wrap it in this sampling framework where I decrement the counter every time I come by this site, and when it hits 0, I collect the information and reset the counter. So this is great because it allows us to take the cost of this instrumentation and scale it as a function of sampling rate. So just by cranking down the sampling rate, I can reduce the amount of time I spend doing this instrumentation. And sampling works very well on programs because they tend to do the same things over and over again. The problem, though, is the framework has an overhead itself. And that framework overhead is a fixed cost. It doesn't scale with the sampling rate. And so thinking at a hardware-software co-design approach, clearly this instrumentation isn't the problem because we can address that by the sampling rate. It's the framework that's the problem. So what we proposed is a new hardware primitive, an instruction called branch on random. So this is a conditional branch, except that rather than specifying the condition for the branch, I specify the frequency that I want the branch to be taken. So the frequency in our implementation is 4 bits, so a value from 0 to 15. And the actual probability of the branch being taken is 1/2 to that frequency power. So we get a range of probabilities from the branch being taken 100% of the time to 0.003% of the time. And the key thing is that each branch can have its own frequency. So we can have lots of these sprinkled throughout the code, and they can all have their own frequency. And the key is this instruction gets a lot less overhead than this sampling framework because, first of all, it's a single instruction. It doesn't use registers. It doesn't access memory. It doesn't do arithmetic. And we can resolve the branch early in the pipeline. And the key is how we generate these probabilities. And it turns out there's a very simple hardware pseudo-random number generator called a linear feedback shift register. So basically, I have a bunch of bits worth of register. And from this, and I shift them over every time I access it, and I shift in a new value, which is an XOR of various other bits. That's not particularly important. What is important is give me n bits of this register, and it sequences through all possible values for those n bits except for all zeros. So if you give me enough bits, the expected value of any bit is 1 50% of the time. And so if I want to get a branch on random that's taken 1 out of every 16 times, I just AND together 4 of these bits, and that gives me a signal that's 1/16 of the time. And then I shift over the register, and again, I have an expected value of getting a 1/16 of the time, independent of the state of the LFSR. So at decode, I extract the frequency from the instruction, and I select the AND gate that has the right number of inputs to tell me whether I'm taken. And the other neat thing is we can just never tell the branch predictors about this instruction, and so it's by default always predicted not taken. So it's correctly predicted without any hardware resources all the time except for the 1 out of n times that I want the branch taken. So the result of this is, compared to a software framework which hits 1 asymptote of performance as we scale the sampling interval, the branch on random hits a much lower asymptote. And we've done these experiments a number of different ways, and what we find is that in practice we get about a factor of 10 reduction in the overhead of the sampling framework. And so what that tells me, or what that seems like an opportunity for me, is that I can sprinkle these throughout my code and collect the information that I want to collect with very little overhead. And for those of you aware of the Arnold-Ryder framework for doing instrumentation, we find that this effect is multiplicative with that effect. So if you also do Arnold-Ryder using the branch on randoms to implement the Arnold-Ryder framework, you get a factor of 10 over what you would have gotten with just Arnold-Ryder by itself. So that's pretty cool. So I can stop here, or I can do 3 slides of where I'm going. So 3 slides. So what I want to do with the speculative compiler optimizations is sort of push the aggressiveness of optimization. So this really nice paper out of IBM by Nick Mitchell and Gary Savetsky about bloat in framework or in applications that use a lot of framework. So they work with these financial customers that are busy slapping code together as fast as they can, and they find that the framework built on top of framework on top of framework to the point where just to extract a few bytes from a SOAP message in order to populate a Java date field, it takes 268 calls and 70 objects to do that transformation. And so the scope of this, so that's a huge inefficiency to this. It's a huge efficiency for the programmer because they only had to write 2 lines of code. But execution-wise, it's a huge inefficiency, but it's such a scope that the compiler just can't wrap its head around it. And so what our hope is that by being able to focus on the small set of paths in this code that are actually getting executed in practice, we can bring that into scope, realize what's actually going on, not really realize, but say this value is being moved from this object to this object to this object. Why don't we just skip all that and move here? And these are the conditions that have to hold that enable this transformation, and encode that as an atomic region with these asserts verifying that those conditions hold. So we'd like to try to eliminate some of that bloat. The second thing is the thing I talked about earlier, sort of trying to virtualize this UFO fine-grained memory protection so that it's useful for multiple applications. And again, the key challenge is knowing when it's safe to clear those bits. And so one of the things that we're playing with right now is trying to para-virtualize this so that things that use those bits don't set them or clear them directly. They go through a software API which decides when to set and clear those bits. And then finally, many of you probably know that Intel and Microsoft recently started this Universal Parallelism Research Center at UIUC along with the one at Berkeley. And one of the emphasis of our center is deterministic languages. That one of the beliefs is that one of the things that makes writing explicitly parallel code in the context of shared memory is the possibility for races. And so one of the big activities is developing deterministic parallel languages that can flag potential races at compile time. And this offers us hardware people new opportunities to support these kinds of languages, both for trying to relax the synchronization that is introduced to avoid these races for increased concurrency at runtime, as well as to exploit the knowledge in the security to optimize data movement to reduce latency for data accesses. So one of the activities I'll be playing in the center is supporting the deterministic language development through hardware mechanisms. So that is what I have to say, and I'm happy to take any further questions. Yep.
The third thing, you said that Arnold and Ryder do not. I had the feeling that it's the same optimization, right? Because you skip all the questions on whether you have to do it or not.
Well, so they're aggregating groups of instrumentation and making the decision once. We're making the process of making that decision cheaper.
Cheap enough. It's almost costless.
So if it's almost costless, so that is a perfectly fine conclusion. It turns if Arnold Ryder gives you a factor of 3 benefit, we get we reduce our little sliver to 1/3 of it was. You might say that's negligible and not bother with the Arnold Ryder. That's a fine conclusion from my standpoint, but they still tend to be multiplicative in our experiments.
Another answer to that, Arnold Ryder is a moderately complicated JIT compilation technique, whereas what you're proposing could be used by random C programmers at the source code.
Right.
It's worth doing both.
Well, I'm not saying it's worth doing both. I'm saying if you do both, you get the benefit of both. But your conclusion of saying that maybe once you've done one, it's not necessary to do the other, or once you have branch on random, it's not necessary to do Arnold Ryder, I'm not going to argue with also. But that's a value judgment, not a scientific statement.
There's various profiling mechanisms that count down hardware performance counters and take a user level trap and do something and reset it to some value. Could you get the same effect by having special purpose performance counters?
So
Just to produce these traps?
The problem with the performance counters is that, in general, so I view the branch on random and instrumentation in general as a nice complement to what performance counters give you. That the performance counters are very useful for collecting low-level information of, I was here, I missed in the cache, I got a branch miss prediction, those kinds of things, very low level, whereas instrumentation is much better at doing higher level stuff, including value profiling, like, I called this function, for this indirect call, it was this specific function that I called, and the two things that I mentioned. So really, I sort of see them as hitting different things. You could have, you could emulate what we're doing in effect by, I receive a random sample and I do a lookup in a lookup table, and if I'm at this particular PC, I collect the size of the heap allocation and where I was. But I don't really know of anybody who's doing that, and it's kind of a pain. Again, sort of what you said, that the mechanism's clean enough that I could add a if 1% statement to my language and boom, code generate it directly. So I need a lot less runtime support to do that. And so what I find in practice is that there's a lot of people that, even though hardware counters would have solved their problem better, they didn't use them because it was much simpler just to deploy the instrumentation.
So have you thought about the issue of an adaptive sampling rate?
Yeah. So self-modifying code plus branch on random gives you adaptive sampling. So, yeah. So that's all right. But yeah, so you could start with 100%, get the first sample, maybe collect a couple samples, and then shift it to 50%, such and so forth. So yeah, so you can get guaranteed sampling, So that, it's definitely something we've thought of. We haven't implemented, but it's sort of, it makes sense, so it should work, right?
So related to Dave's question, can you take the hardware counter and just take the 4 least bits and do an end of them and consider that random?
So the thing about that, so the property we get from the LFSR is what gives us this, that each branch can have its own frequency and they're independent. So if I just have a counter and I have two, that if it's a counter and I'm the only branch on random in the code, I will always get the nth sample. If I have another, you can think if there was a loop and I had two branch on randoms in the loop, I would get a sample every n over 2, and the other guy wouldn't get any, perhaps. That there's some interference between that if you implement it as a counter rather than an LFSR, you tend to get interference between multiple branch on random sites that you don't get with the LFSR. I don't know if that makes sense. The other thing you get for free is that, and I actually can show you this. So we did some accuracy numbers also. Let me go ahead and close this. One of the things that's, is this the right one? No. No, it must be it. Doesn't look right. Yeah, I think that's another. So in one of the benchmarks, we had that there was, if you used a counter, there was something in the program that happened at that same power of 2 kind of frequency, and so there was this resonance sort of between the program behavior and the sampling rate. And the thing about the LFSR is, even though I'm sampling 1 out of every 16 times, for example, it's not every 16th time, and so the likelihood that I get some resonance is a lot smaller. There's still a chance because it is a probabilistic, it's a deterministic sequence, but it's a very small likelihood. So I think there's really no reason not to use an LFSR over a counter because it gets better properties and it's no more expensive. It's actually potentially cheaper.
So let me stop it right there and thank Craig for a very interesting talk.